Good afternoon, class. Thank you. You can sit down. All right, then. I started the lesson on similar figures and similar solids in our previous lesson. We'll continue from where I stopped on that. All right, then. On the monitor, as you can see, I've got two solids. We'll be talking about similar solids because I went through similar figures already. Hopefully, you've got the notes down in your exercise book. So similar solids, on similar solids, it says two solids are similar if the ratios of their corresponding linear dimensions are equal. And when that happens, the surface areas of similar solids are proportional to the squares of their linear dimensions. I'll explain when you see the diagram next. And then for similar solids as well, the volumes of similar solids are proportional to the cubes of their corresponding linear dimensions. I'll explain further. Okay, if these two cuboids are similar, these two cuboids are two solids, there's A and B. That means the ratios of their lengths should be in the, their lengths should be in the same ratio. So as you can see, this height is in the heights are in the ratio 4:2, which is the same as the ratio of their widths, which is 2:1, which is also the same as the ratio of their lengths, which is 6:3. So their corresponding linear dimensions are proportional. They're supposed to be in the same ratio. Okay, if we go back, that's the first thing there. It says two solids are similar if the ratios of their corresponding linear dimensions are equal. Okay, we look at what happens to their areas. Okay, I actually went ahead and calculated the surface area of these two solids, but if you can look at just the area of the front face first. Okay, the area of the front face of this one, the area of just the front here, see, it will be 6 times 4, which is 24. The area of the front face here is going to be 3 times 2, which is 6. Now 24 is to 6. Is the same as 4:1. Okay, the ratio of this will be the ratio of the area, so what I would call the area ratio, and then the length ratio, as you've seen, is 2:1. Okay, then I went ahead and calculated the surface area, and you all know that this cuboid has 6 faces, one at the front, one at the back, 2 on the side, 1 at the top and 1 at the bottom. So if there are 2 faces that are the same, and that's I multiplied 2 by each of the areas of each of the faces. So the first one, 4 times 2, is the area of this, and I multiplied by 2 to get that. Okay, then the area of the front, the top, which is 6 times 2, which is the same as the area of the bottom, multiplied by 2, and then 4 times 6, which is the area of the front, and the back, I multiplied that by 2 as well. When I did that, I got the surface area of this one to be 88 square centimeters. I did the same to B. Okay, there's 2 faces that are the same as the front, which is 3 times 2. I multiplied that by 2, then 3 times 1, which is the bottom and the top, multiplied that by 2, and then the sides, 2 times 1, I multiplied that by 2, I got 22. Now 88 is to 22 is the same as 4:1. So the ratio of the surface areas, or you could also say the ratio of the front face, is 88:22, which is the same as 4:1. Okay, you will also note that this ratio is actually the same as 2 squared is to 1 squared, which is 4 is to 1. And 2 is to 1 is the ratio of their lengths. Okay, I explained that a little bit as well in the previous lesson when I looked at the area of the rectangle that was on the board. Okay, so what actually happens here is that to get the ratio of the surface areas, instead of calculating the actual surface areas, you just square the ratio of the lengths, because 2 squared is 4 and 1 squared is 1. Is that bit clear? Okay, next one, we look at the volume. The volume of A is 6 times 2 times 4, which is 48. The volume of solid B is 3 times 2 times 1, which is 6. And if you look at the ratio of the volume, that's 48 is to 6, which is the same as 8 is to 1. Okay, so according to what's on the monitor, the volume ratio is, I think, 48 to 6, which is 8 is to 1. And 8 is to 1 is exactly the same as the cube of 2 is to 1. Okay, because 2 is to 1 is the ratio of the lengths. You cube that and you get the ratio of the volumes. And if you can just go back, it says for similar solids, the volumes of similar solids are proportional to the cubes of their corresponding linear dimensions. Is that clear? Okay. Now, I've just done a summary on what I've said. If the length ratio, or if the ratio of the length is x is to y, the ratio of their area, whether it's the area of the face or the surface area, will be x squared is to y squared, and the ratio of the volumes will be x cubed is to y cubed. Okay, having said that, let's look at the example, or two examples actually, on the board. All right, in a scale model of a school, the area of the assembly hall is 1/100 of the actual area. And you all know that a ratio can also be written as a fraction. You are asked to calculate the ratio of the volume of the model hall to the volume of the actual hall. Okay, that means the ratio of the volume, the ratio of the areas, the area of the model to the area of the actual area, that's the area of the assembly hall, is 1:100. Okay, that would be the ratio of the area. Okay, the ratio of the area would be 1:100. Now, to get the ratio for the length, it will be the square root of 1 to the square root of 100. Just like, for instance, here, if you were given the ratio of the area, which is 4:1, to get the length, you will have to find the square root of 4 and the square root of 1 to give you the actual length ratio, because you cannot use the ratio for area to find the length and vice versa. You cannot use the length to find the area, the length ratio to find the area. You have to find the area ratio from the length ratio and then use it to find the area. So here, I cannot use 1:100 to find the ratio for the volume, because that's the ratio for the areas, 1:100. So to get the ratio for the length, I will have to find the square root of 1 and the square root of 100, and I get 1:10. Because it's the length ratio that I cube to find the ratio of the volumes. So 1 cubed is to 10 cubed. I've got 1:1000. So that is now the ratio of the volume of the model hall to the volume of the actual hall. Is that clear? Okay. Next question. The volume of a cone of height 4.2 centimeters is 210 cubic square centimeters. It says find the height of a similar cone whose volume is 60 centimeters cubed. Okay, that means the ratio of their volumes would be 210 is to 60. Okay, that's also simplified to 7 is to 2 if I'm correct. Okay, I divided 60 by 30 and got 2, divided 210 by 30 and I got 7. Now that is the ratio of their volumes. I cannot use the ratio of the volume to find the height because I'm asked to find the height because the height is a length. Okay, there are actually two ways. If you know the formula for the cone, then you can use it. Otherwise, it's not necessary. What you can do is to get the ratio of the height, you just find the cube root of the ratio of the volume, because that's what I state here. You cube the ratio of the length to give you the ratio of the volume. So what you do is you find the cube root of 7 and the cube root of 2. So the volume ratio will be the cube root of 7 to the cube root of 2. Okay, so we are going to use that. Okay, the bigger one has height of cube root of 7. No, the smaller one, and then because that's the bigger one. That's the one that has a height of 14.2 has a volume of 210. Okay, this one is supposed to be just 14.2. Okay, so I've got the cube root, the ratio of the height now is the cube root of 7 is to the cube root of 2. I just wanted to leave it like this so that the answer will be a little bit more accurate. And the height of the one that has a volume of 210 is 4.2. Then I have to find the height of the other one. So I can write it as the cube root of 7 over the cube root of 2 is equal to 14.2 over x. And then you can use your calculator. The cube root of 7 multiplied by x is equal to the cube root of 2 multiplied by 14. Okay, x is the cube root of 2 multiplied by 14.2 over the cube root of 7. Okay, see if you can help me calculate the answer to this. Okay, note, you'll have to find the cube root of 2, multiply it by 14.2, and then divide the answer by the cube root of 7. However you do that on your calculator. $9.35. Everyone got 9.35? Okay. All right, is that understood by everybody? Any questions? No? All right, you are going to start with question 1 and question 2. Let's have a few answers. I hope you have only one. Any volunteers to give us their answer? For number one. Anyone? Patrick? Yeah.
12 centimeters.
Okay, Patrick's got 12 square centimeters. Any other answers from apart from 12? Jake?
24.
24? Any other answers? Who's got a different answer apart from the two that are on the board? You have one or the other? Okay, let's see. A triangle of base length 3 centimeters has an area of 6 square centimeters. What is the area of a similar triangle of base length 6 centimeters? So, the ratio of their lengths is 3:6, which is the same as 1:2. All right, I said do not use the length ratio to find the area. So what you need to do is to find the ratio of their areas. So the ratio of the area will be 1 squared is to 2 squared, which is 1:4. So 1:4 is equal to 6 is to what? So I get 1/4 equals 6 over x. 1 times 6 is 6, therefore 4 times 6 is 24. So x is equal to 24 square centimeters. So the answer is not 12. Those of you who have 12, that's because you used 1:2, which is wrong because that's the ratio of their lengths, not the ratio of their areas. You're supposed to square the ratio of their lengths to find the ratio of their area. So the answer is actually 24. All right, do number 2. All right, a trapezium of area 8 square centimeters is a perpendicular height of 4 centimeters. A similar trapezium has an area of 18 square centimeters. Calculate the perpendicular height of the larger trapezium. Geno, what's the height of the trapezium?
6 centimeters. 6.
6 centimeters. Has everybody got 6? Okay. All right, the ratio of their areas will be 8:18. If you cannot find the square root or the cube root, try and simplify. The reason why I got the cube root of 7 and the cube root of 2 just like that is because I couldn't simplify 7 and 2. That's the smallest I can go. But 8 and 18 you can. 4:9. So the length ratio is going to be the square root of 4 to the square root of 9, which is 2:3. And that's the ratio you use to find the height, because the height is a length. So 2:3 equals 4:x, and x happens to be 6. All right, one more before you go. This one is very easy. You can just read it and know the answer straight away. Oh yeah, it's that simple. If it takes you more than 2 minutes, then all right, number 327. If 64 is 4 cubed, then all you have to do is cube 3. You get 27. What about number 4? You're still working on number 4? Okay, I'm going to have to let you go. For homework, you are going to do question 4. That's still part of question 4. And question 5. And then question 6. 3 questions only for homework. All right, the key word to the pilot teacher is solids. Good afternoon, class. Thank you.